where we left off last time. So we spoke about local inference, about revision within concepts, and a week before we talked about the control system, and 1 week before we talked about the memory structure of the system. And if we go back to the control mechanism, we see that all the inference only happens if there is a shared term between both premises. And this is an issue for temporal inference, because if you have events, there is no guarantee that both events will share a common term. For instance, let's start here. For instance, if you have something like switch 0 is on, so we have an event like that, and we have a different event which says that 1 is on. In this case, both events share a common term which is on, but it doesn't necessarily have to be like that. It could be some other event, like I hope that's quick enough. So the day is rainy, and then we could have something else like the street is wet. And in this case there is no common term in the events. There is no common subterm in both premises, but we still want to do inference, and a very important inference is called temporal induction, that if you have event A, and you have event B, and you know that event B happened after event A, you can derive the conclusion like that, which says A leads to B. With the induction group function. So this is an issue because the memory structure we saw only connects concepts when they have a shared term. For instance, cat, the concept of cat is connected to the concept cat is an animal, but in this case there is no common term. So somehow we have to support this type of inference. And in openness we do this with an additional bag, and this bag stores all the incoming events. For instance, if this is the global picture. Where we have some memory. And we always select two premises for inference. That will go back into memory. We additionally have something called event back. Which stores events, for instance A and B, according to the priority values. And this data structure for events allows us to perform this inference. And the way it does this is the following. There are, let's say, A was observed, so event A enters the event back. So, now B comes into the event back and selects a second premise for inference, which in this case would be A. So B comes in. And before it enters the event back, it triggers inference with an item in the event back that is already in, based on the priority value. So we get something like AB. Which then goes into memory. So it's so our event inputs or input events first go to event back. Additionally, the incoming events also go into memory. So there will be a concept A and B in memory that will also receive those input events as input task. So what we had last time would only capture the last part. That when there is an input event, it would go to memory and create a concept and would be added into the belief table of that concept and so on. But to support this inference, it also goes to the event back, and this allows to create statements like this one. But there's an additional thing which event back does in openness, which is called segment formation, or in some kind of intersection, which is the following inference or AB where this is a segmental conjunction, where we use intersection. And conclusions like this sequence additionally derived. So we have the temporal induction result, which goes into memory. This one does not go back into event back. And we have sequences that will be derived. Sequence event, which is a form of compound event, which will go into event back. And we have added this structure to allow temporal conditioning to happen. For instance, if there is a event C, this event C could now perform inference with the compound event AB and derive a temporal implication like A and B in this sequence together leads to C. And this result would not go into event back, but the same as this implication would go into memory. When the sequence ABC will again be a compound event that goes into event back. So in this design, the event back is only used for two purposes. First, to group events together, and second, to allow temporal induction between events and compound events or sequences.
So the current implementation is this event back defined over the whole system, or is for each individual channel?
Currently, there's one global event back that is where all channels report the results to. So if there is something like a separate channel, something like a vision channel, then the results from vision channel would go into event back as a result. For instance, in our example which we had, we would have something like with our matrix terms. We would have something like that. And zero bread, which would be an event, which is a composition of many of all the, how should I say, it would be a result that's generated by the vision channel, which will then go into event back. And so all events that go into the system, even when multiple channels are attached, the results of the channels will always be combined in event back. So it's like
yeah, I agree. There should be a cross-channel event back. My real question is whether we want a two-level structure. That is, we have an internal event back for each channel. So we combine those things within a modality first. Then we do this cross-modality combination.
Oh yes, this is happening. So if we have pixel number events, they will be merged by the vision channel to be combined to a single matrix.
Yes, that's what I mean.
Like this one. So within a modality, there's also some kind of accumulation of information, some kind of how should I say, a way for events to be combined.
You see here, basically what we're doing here is not really reasoning in the traditional sense. It's more like the self-reorganization of the signals, right, into larger chunk. So for that kind of thing, we may expect a two-level structure One is within each channel, which with more details. And then across channel, typically only the major events, the more important events, will be taken into consideration. Otherwise, there will be just way too many of them.
Exactly.
To make sense. So good. Another question is the priority value in this event bag. What do you put in terms events, right? But are we using the same priority calculation for events here and events everywhere in the system? Or here we need something special?
But it's going here, when an event comes into the system, into the event bag, sorry, it moderates the priority of the item based on the concept priority. So
based on the concept priority, okay.
Uh-huh.
And what I'm asking is, actually previously I think we talked about this idea, we are thinking this as a queue, not as a bag. Because if we have a queue, then I think we remember, I remember we talked about, for example, if you observe A, B, C, D in that sequence, what you try to do is build a temporal relation between A and B, B and C, C and D, rather than with A with everything following because there are just too many combinations. I can see the point of changing that queue into a bag, but if you're doing it in a bag, we still want to keep that time factor. For example, if you have something which is immediately followed another thing, and then there is a higher priority for this tool to be combined together than with this and something remotely following it.
Oh yes, but this is also happening in event bags because the items are constantly forgotten, so the highest priority items in the event bag are
Okay,
usually
so it's okay. So we're using that.
So it tries to.
Of course.
It tries to integrate both to make sure that temporarily close events have a high chance to be.
That's a good point. So the forgetting already handled that for us.
Exactly. But additionally, it also tries to incorporate the concept priority of that event.
Yeah, of course, of course. That's the attention, your anticipation, everything will be in concept priority.
Exactly.
Of course. Yeah, that's good. That's nice, actually.
Thank you.
That's nice. But when you calculate, when you form this temporal implication, will the priority anyway depend on the temporal distance between A and B or not?
Yes.
I think it should.
It does.
Okay.
It's also because what it also does, the drop value of the implication also, it uses a projection of the drop value from the second event to the first.
Yeah, because otherwise there is a confidence decay, right? If you project to very far. Okay, good.
And the total picture we want to have is something like this. We have nars. That is another one. There is nars with some, let's call it some kind of cross modality combination which we reach with event bag, and then we will have different channels for like vision. Even the vision channel might itself be separated into 3 channels for red, green and blue, for instance, and we might have something like a sound channel. And so we have some kind of hierarchical composition of different channels for different modalities that will at some point be merged into some kind of cross-modality experience. And
you just whether we should treat it as a queue or as a bag.
That's true.
Yeah, most people in most of the models for this kind of thing, I guess they're going to treat it as a queue. to keep the temporal order. But I think we have reason to treat it as a bug because the temporal information is still there. But we are going to stress this priority ranking.
At least the structure allows to have some kind of top-down attention where the concepts, for instance, events that are related to a war will automatically get a higher priority just because the concept will tend to have a higher priority. So we automatically get a way for concepts to influence which events will be related with each other and which one will have a lower chance to be considered. So this is one nice property of the event bug.
You see, actually in this way, this event bag, this global event bag, will be naturally related to the notion of like a global working space or even consciousness model or whatever in a system. That's what the system feels at the moment.
There's also the big question because ideally the event bag would also contain derived events, but currently it does not. Currently it only allows input events to enter, but this is something which we really want to extend, but it, whenever I allowed derived events to be part of the event package, it was difficult to make sure that it still considers input events too.
That's exactly something I want to discuss next week. But today, let's just focus on temporal reasoning.
So
question over there.
No questions. I find it's a little bit difficult to recall the negative evidence. For instance, for example, if the B comes after the A, but later there comes the A again, but there is no B after it, but it won't record a negative evidence, but when we do the merge, it will need trouble.
I agree. It's important for it to see negative evidence for such hypothesis. And this is the next thing. Indeed, because this mechanism, as we have here, only allows to see positive correlation. Like whenever A leads to B, it will be, then this hypothesis will be positively reinforced. So, but often and interestingly, for conditioning, it's necessary to see negative evidence. For instance, if we have a sequence like that, A, B, C, one of my favorite examples because it's a really simple thing that shows something very interesting. B, B, B. For instance, if we have a sequence ABC, ABC, and then something like BBB, AAA, we want the system to see that this relation that B leads to C is not as successful as this relation, that A and B together leads to C. And because, and how can we learn this? How can the system learn that A and B together leads to C while B alone does not? And this is exactly the thing that it needs a way to see negative evidence for this implication. So that when next time B comes, but C will not be there, it will see this case as a negative evidence for this hypothesis. And this we do with so-called anticipation, that when next time the B occurs, the system with those two premises will derive C. It will predict C to happen after B, because of what it has observed in the past. But this time C won't come, and the system notices that although it has predicted C to happen, C is not happening. And this is where the system finds the negative evidence for this hypothesis.